The broadcast is now starting. All attendees are in listen-only mode.
Good morning, good afternoon, good evening, everyone, wherever you are, and welcome to today's technical webinar. My name is Melad, and with me today is Rahul, and we're simulations engineer at LaunchTech. And today we will be presenting to you a technical webinar on the title of bird strike simulations using Abaqus finite element analysis software. Please feel free to drop down your questions on the right-hand side on the questions or in the chat box, and we will come back to your questions at the end of the webinar. Now, a recording of this session will be provided after the webinar and will be sent to you over email. If you did not receive it, please feel free to reach out to us and we will give it to you. Now, before moving on, I would like to quickly introduce our company, LaunchTech. LaunchTech is a UAE, Abu Dhabi-based engineering company specialized on mechanical engineering and advanced finite element analysis. We have a strong partnership with Dassault Systems, and we're the official distributor of Simulia software, as well as the development and service partner of Dassault. The services we offer are the distribution of Simulia software, like I said. Also, we provide technical consultancy on finite element. We also provide technical trainings delivered by certified trainers, as well as certification exams to get you certified and increase your credibility. Now, the brand of Simulia includes several software, and it offers an advanced simulation product portfolio while covering many disciplines for a true multiphysics simulation. It starts with the most known Abaqus software, moving to EyeSight for parametric optimization, and then Tosca for topology optimization, FE Safe for fatigue simulations, and SIMPAC for articulated systems. Then PowerFlow and XFlow for CFD, and CST finally for electromagnetic simulations, and there are a few more software. So now moving to the technical content of the webinar. Now, the bird strikes are basically the collisions between birds and any other wildlife with the aircraft, which are known to cause loss of lives and substantial losses to the aviation industry. Of course, this is in terms of cost and damages, as well as delays every year. And it's important that we mitigate and predict and prevent such mishaps from happening, as this annual damage is estimated to be around $1.2 billion every year. A notable incident is the one that happened in 2009, flight number US 1549, where the accident happened after both engines failed following a bird strike shortly after takeoff, and it ditched in the Hudson River between New York and New Jersey. And this is what the movie Sully, if you're into movies, was based on. So to prevent such events from happening, there exist passive methods to reduce bird strike occasions. And one of them is to scare birds off by firing air cannons when birds are present in the aircraft activity. Another approach could be to alter the airport, the nearby landscape of the airport, to be less bird friendly. And this is done by usually filling in the ponds and replacing the grass with gravel. Another approach can be to also do some experiments as per the regulatory bodies of Federal Aviation Administration. And these physical certification tests are done with real birds, sometimes with frozen chickens, and they're quite expensive and time-consuming. Now, in this webinar, we will not discuss any of these approaches, but rather we will be discussing the simulation part on how do we reduce experiment and complement it with our complement simulation with experiment. Now, the simulations on this industry has been used for over 30 years to design bird-proof designs. And on this webinar, we will be scratching the surface and providing an overview on the development of such technology. And before moving on to the live demo on Abaqus, I'd like to present to you some of the necessary prerequisites in terms of knowledge and material modeling. So when it comes to the demo, everything should be clear. Now, you may be asking yourself, why is this simulation, how can it be costly or time consuming? Also, I mean, why is it difficult to do? Why do not many people do it? Now, this is because such simulation is highly prone to errors. It can be very difficult to master, but once mastered, it's extremely useful and efficient along with experiments. And it's difficult because it's highly dynamic events, as you can see on the animation on the right. And it also includes extreme deformations and failure to the composite material of the air structure. The other difficulty is modeling the material itself, which is the biological material of the bird. And this is difficult because, as simple as it sounds, a bird is just a bird, but it composes of many materials like flesh and blood and the beak and the feathers and so on. So it's really, really difficult to model the bird as is. And so in certification tests, they actually use a frozen chicken. And on simulations on bird surrogates, we use what we call a cylindrical body with hemispherical caps. And we usually assign gelatin as a material to this shape, because gelatin allows accurate prediction of both the shock, which we call the Hugoniot, and the steady state flow pressures with good accuracy. Okay, so when we speak about bird strikes, it's extremely important that we also shed some light onto the shock waves. And the study of materials under shock waves means that it changes in configuration and in geometry from rod into a plate geometry. And these shock waves occur when a material is stressed far beyond its elastic limit by a pressure disturbance. So this pressure that is usually generated by the shock wave can exceed several orders of magnitude in the material strength, the property of the material. And this is why we can view the material as a hydrodynamic material. So it's more like a soft kind of material, unlike ductile metals, for example. And the strength effects of such material would only take effect at a later stage of the event, once the shock wave reaches a steady state pressure. Now, the complex definition of the Hugoniot pressure by itself is not enough to fully characterize the material. And what's really important in defining such material is the equation of state, what's referred to in Abaqus as EOS. And this is something that Rahul will explain in the live demo. Okay, so how can Abaqus and Simulia portfolio assist in such problem? And now Abaqus provides, as most of you may know, Abaqus Explicit Solver. And the Explicit Solver is preferred over implicit in such problem because of its robustness of solver, as well as its cope with large displacements over small time increments. And so while using Explicit, there are several formulations that can be used to capture the spraying of the bird very well, as you can see in this image. The three main formulations are Lagrangian, SPH, smooth particle hydrodynamics, and CL, coupled Eulerian Lagrangian. And these three prominent formulations are very typical and are best practice within the industry. Now, but the question is, how do we know which one do we use? What do we do with these? How do we know if this is right once we select it? There is no rule of thumb here. Usually it's with comparison with best practices and with the experimental results. As we always say, simulation complements experiment. It does not replace it. So to begin with, I'll just shed some light onto each of the formulations. The Lagrangian, this is the traditional finite element approach, and it's the conventional way and simplest way that usually comes with limitations. Limitations being especially at high deformations. So when the mesh is distorted highly, as you can see on the animation on the right, the Lagrangian does not capture it very well. And this is evident because you cannot see the spraying of the bird. So we can say this is quite limited and it's very uncommon to use for bird strike simulations. Moving to SPH, smooth particle hydrodynamics. And this addresses the modeling needs in case when Lagrangian becomes inefficient or it cannot cope with the problem. And this is extremely useful for violent fluid flows, such as the bird, and where mesh or grid-based CFD cannot cope. So the novelty of SPH usually, specifically lies in the method that's used for smooth interpolation and differentiation. And this is what we call the smoothing function. And this smoothing function is what defines the neighboring particles interaction with each other. And this method captures the spraying of the bird very well, and it's continuing to gain popularity most of the time in bird strike simulations. Of course, these nodes are free to move, so severe element distortions are avoided. Hence, the formulation allows for capturing those high strain gradients very well. Moving on to the last formulation, the coupled Eulerian Lagrangian. This method usually means that the material flows through the mesh and the mesh is not distorted. And this allows for simulating high distortion problems with ease. So I'll give an example of the rivet here. So the goal of this simulation is to determine the strength of the riveted joint, including effects of riveting forming process. So as you can see on the Lagrangian formulation, the mesh is highly distorted at the corners, which induces inaccuracy in the results. Whereas if you model the same problem using CEL formulation, as you can see, the distortion is well captured and the mesh is not highly distorted. And this produces more accurate results compared to experiments. And this method, CEL, is exactly what we will explore in our demo on Abaqus. Now, before I leave the floor to the demo, one last point I want to highlight is the composite structure and the class of composite material within the aerospace and aviation industry, as it plays a significant role in current and future aerospace components. And it's particularly attractive because of its weight and the strength to weight ratio as well, and stiffness to density, not to forget. Now, the modeling of such structure or the fuselage is out of scope on this webinar, and we will mainly focus on modeling the bird, the biological material of the bird. I will now leave the floor to Rahul to demonstrate to you on a live Abaqus demo how to use CEL, coupled Eulerian Lagrangian, to model the bird strike. Floor is yours, Rahul.
Hi, good afternoon, everyone. I'm Rahul, and today I'll be explaining to you how to actually simulate the bird strike model on an aircraft using Abaqus Explicit. The case study for this is that we're going to use two birds that will come in contact with a double-shelled aluminum-based fuselage. And we will, as Melad explained, we will be using the combined Eulerian Lagrangian model. Before I start, I have 1 minute. Issues, 1 minute. One sec. I'd like to apologize for that. I don't know what went up. Okay, so here's my Abaqus GUI. Before I actually start, I want to inform that since we're not really going through everything with the geometry and the material of some parts, I've already created a Python script which will declare those models in this Abaqus GUI. So for the parts, I've already created my bird, which, as Melad explained, we will be using a cylindrical shape part. The panel, which is basically a quarter section of the airplane's fuselage. And as Melad explained, we need to use the Eulerian domain to encapsulate that bird into the Eulerian domain. The thing with the Eulerian domain that you should know is that we're not really using the bird with it. We are just blending the material of the bird's geometry into that Eulerian domain. And that is why it's important to create a discrete field within that Eulerian part. Another question maybe many of you ask me is, why did I create two cubes for it? I actually used one part, but I've partitioned the part in two so that computationally it'll be cheaper for me to model one Eulerian domain for the first bird, which is situated at the left, and the second Eulerian domain, which is situated at the right. I will just explain to you how to actually create that Eulerian domain. You just have to double-click parts. There will be an option here which shows a modeling space. Select 3D, The only thing you need to change here is your Eulerian from deformable and then create the extruded solid. Now, based on the dimensions of your part, mine is in meters, so I just needed 5. I press continue and I just went on with the geometry. Since I've already created it, I'm not really going to go forward with that process. I'm going to now move forward to the property section of the model. So for the properties, as you see, I've already created the aluminum material, which is needed for the airframe panel. I'll be using the normal density, elastic, plastic, and ductile damage. Density is important, as you know, it is required in a dynamic explicit analysis. The only thing I'll create here now is obviously the Eulerian domain. And for the Eulerian domain, I will name it bird. Since it's dynamic, I will go with a density behavior. And since we can always assume that the bird is 75% water, 25% mass, we can assume safely that it's more fluid than solid and it's more water-based. So we can assume that the material we want to use is water. So I'm going to give the mass density of 1000 kg per meter cube. After that, I will now go with, as Melad explained, to give a behavior of the shock waves called the equation of state. There are many options of equation of state. However, we're not dealing with explosive or thermodynamic reaction. We just want to deal with shock waves. So as the slide said, polynomial Lagrangian method would be preferred in this case. So I will use the differential US minus UP method. CO here is actually the reference speed of sound at the medium. For water-based materials, you can say that it's about 1500 meters per second. So I'm going to add that there. And since I'm not really interested in the constants for the sake of the webinar's complexity, I'm just going to add the constants to be 0 for the S and 0 for the gamma. And I accept that as my material for the bird. I then move on to the sections option where I have to create my Eulerian section. I'm going to create that by naming this an Eulerian domain. I'll give it solid and I will change my type to Eulerian and I press continue. It'll ask me for the base material and the instance name. So I'm going to name the base bird as the bird's material suggests, and the instance name is automatically given as bird1, which I'm going to accept it as a default. And with that, I've already created my Eulerian domain. The last thing I need to do is I need to assign that section onto my Eulerian domain. So I'm just going to double click the section. It tells me to use this. So I'm going to say yes. And that's my section done. Another thing I want to do before I move forward to the meshing part is I like to create sets, because when you look at it in a code-based point of view, the lesser sets you create, the lesser the equation will be complex. So I'm just going to create Eulerian left for the left section of my Eulerian base. I'm going to press continue. And then using the selection part, I'm going to create the left cell as my Eulerian left. I then move forward to the Eulerian right. And then using the cell selection, I'm going to create my right domain. And finally, I just want an Eulerian hole. So I'm just going to create that set as well. So I'm just going to name it Eulerian hole. And I'm going to select both my sets and I'm going to accept it. And that basically ends our parts and property. Usually what happens now is that when you create your Abaqus model, you don't really go with, like, especially in CEL models, you don't really go with assembly step interaction. You first go with the mesh, because in what we are going to do, some of the loadings and boundary conditions or the predefined fields here require the mesh to be included in it. So I'm going to go on to my mesh. And as you see, this is my Eulerian domain. Here's the part. And before I go with seeding and all, I first want to see the type of shape and the element type it is. So I go on mesh and I go on controls. I click both my Eulerian cells and I press accept. I see that it's hex and structured, so I'm pretty happy with that type of mesh shape. So I'm going to press OK with that. Now I go on to the element type. This is important because when you go on to the element type, you need to make sure that the element library is explicit and Eulerian. The new releases, Abaqus has an algorithm to already automatically recognize that. So it's already given for me. So Eulerian, linear, and for the sake of the webinar simulation, I don't want to spend time on calculating second order accuracies. After that's done, I just seed my part. I will give it maybe approximate global seed size of 0.01. I'm pretty happy with that seed, and I'm going to go along with meshing my Eulerian part. That is basically the mesh for the Eulerian part. The only thing I need to do now is to mesh with the panel, which I have done. I just want to show you the controls. I have kept it a quad structure. And for the element type, I have to make sure it's explicit since it's a dynamic analysis, linear, and I've left Abaqus to use the defaults for the simulation. Now, there might be questions on why I don't need to mesh the bird. As I said, the bird's material is blended into the mesh, so I don't really need to mesh again for the bird. I'm just going to make the bird a discrete field so that the material is assigned to the bird. I don't need to mesh this. And with that, we are effectively done with our meshing, and we can go ahead with the assembly. I've already used the Python script to already create the instances of the bird model. And as you see here, you don't really see where the part is, but if I keep a translucent option, you can see that this is the Eulerian domain, and within that domain is the bird, which one is going to be traveling vertically to the fuselage. The other one will come horizontally, and we will see how it actually affects the fuselage once the bird impacts that structure. Moving along, I will also just give you a general idea of the step commands. So I've used a dynamic explicit, as I've mentioned earlier, with the time period of 0.0015. I don't really want to bother much about damping and all at this rate, so I've left the defaults for the bulk viscosity ratios. The only thing I now need to add is a field output request for my panel, because I want to see really what happens to the results of the panel once it's broken, once it's in impact. So I'm going to go to domain. I'm going to use a set, and I'm going to create a set for the panels. I want to go to displacements, and I'm going to click Hue. This gives me the translation and rotations of the panel after the bird has impacted, as well as I want to go through the failure, and is it failure or stat, or is it state? No, sorry, it's state. So I want to go on state, and I want to create a status field so that it shows some of the failure and plasticity models. And I'm happy with that. I'm going to just click OK. And that really concludes our step field for it. We now go forward to the interaction module. For the interaction module, I have already used the Python script to create a no friction property by just creating a property and not assigning any value, since Abaqus already assumes that to be frictionless. I then use this friction property to create a general contact step, which is an easy method to just let Abaqus decide when the contact is made, what mechanics to use at that moment. So I use the general contact, I gave it the all with self, and then I assign the global property assignment to no friction. And that concludes basically our interaction module with this. Now, when we go on to the load, boundary condition, and the predefined fields, I don't really want to create an external force, because that already it will conflict with the actual idea that the bird is already in motion and not something that we are actually exerting motion to. So for that, instead of creating a load, I'd rather create something called a predefined field. We also need to create a predefined field for the discrete method. So for that, all we have to do is we need to go to tools. We go to this option called discrete field, and we create something called a volume fraction tool. Now it asks me to select the Eulerian part instance. I'm going to press instances, and I'm going to create my Eulerian domain. Then it asks me to select the reference part, which is basically what you want to blend into. So I want to blend, let's say, my bird 1 into it, and I'm going to press OK. It's going to give me this field. I'm just going to say, all right, I'm going to call it discrete left. Usually for accuracy, it's best to keep it high so that you have, so that the discrete field's accuracy is high as possible to give the best results. And I want to create a node set for this discrete field. So I'm just going to call it bird left. And that basically creates my discrete field at the left side. The same thing I really want to do with the right also. So I'm just, So I'm just going to go to tools. I want to go to discrete field again and go to the volume fraction tool. I then go to instances to change my to check my Eulerian domain, and then I go on to the instances again to tick the bird right. Abaqus will give me this option, and I'm just going to name it bird right. I want to give the accuracy as high as possible, and then the node set I'll create it the bird right model. And that basically concludes my volume fraction step. Now, all I need to do now is to create those predefined fields. So I'm just going to double click my predefined fields. And then I'm going to give my option as material assign. I'm going to go to my initial step. And then I want to click material assign in the other category. I press continue. It asks me to select the Eulerian part. So I'm just going to select the Eulerian part here. It gives me this option where I can create my regions and sets. So instead of going for uniform, I've already created my discrete fields. I go on discrete field. I select the region to be sets, and then I go with highlight to just highlight my port. I go Eulerian left. I go continue, and then I create my discrete left. So that's done. And since I need another for the right, so I'm just going to go to the right, go to regions, double click that. And then I want to check my discrete right bit, which is highlighted in pink. So I'm going to go continue. And the set I want to create is the discrete field I want to create is bird right. I'm pretty happy with that. And I'm going to create my default options. The second thing we also need to consider is the velocity of bird. As I mentioned, I'm not going to create an external force to create that. I'm going to create a predefined velocity for it. So I'm just going to double click predefined velocity. I'm going to call it velocity left. And I go on mechanical and the velocity. Like I said, I created the node set for the reason that I can create bird left. I go continue. For the bird left, since it's going to the horizontal Z direction, I will want to give it a speed of, let's just say, minus 210 meters per second. And I'm okay with that. And then create a velocity right. And the same option, I go with category mechanical, type of selected step velocity. And then I create bird right on the node. And then I'm happy with that. Now, since this is moving at the second direction, the y direction, I should go V2. And I want to give this a step of minus 160. And that basically ends like my manual inputs to the assignment. I'm pretty happy with this. So what you should always do is just save it. Go to the jobs, create the job, naming it anything. So I'm just going to name it bird test. I'm going to continue with that. I have some processors. I'm just going to name it 6 and go with it. And that's how you basically create your CEL model for this for the bird strike. I don't want to submit it now because it takes a lot of time. So I'm just going to go ahead with the results. I have another set of results with me, and I'm just going to go to that. So as you see, you can see the Eulerian domain here. You don't really need this Eulerian domain because it will be recorded with the volume fractions I've created below. So I'm just going to go on tools. I am going to go on view cut, manager, EVF void, and it gives me this. Now I want to plot the contours of the volume fraction, and as you can see, the volume fraction immediately shows the bird deforming. And let me just play an animation to show what really happens when it gets contact with that. So I want to actually show you what really happens to the stresses on the panels when you get in contact with that. So that's my S value, my Mises stress, and this is what happens. You can see that with high deformation, the Eulerian is able to still not have any issues, and it's able to deform and create that damage onto that panel. If you see the other, if you see the bird, it's, the shock wave is so much it's even able to go towards the second panel and damage that as well. And this actually shows how devastating an aircraft damage can be due to these bird strikes, and why we really need to simulate them more often. With that, we actually end the demo. I just want to explain to you another thing about why we prefer the CEL model over Lagrangian. So I took the time of doing both a CEL and Lagrangian model. I want to show you the simulation of the CEL model. So I'm showing you. It's not playing, so Melad, if you have this slide, can you play it as well? Because I don't know why it's not playing on mine.
Yes, I do. I can play it on mine.
All right. Sorry about that. I don't know what happened. Yeah.
Presenter view, please.
Yes, I will.
Okay. Are you able to see my screen?
Yes.
Okay. Okay, thank you, Rahul. As you can see on the CEL model on the left, the high deformations are well captured, and the scattering and the spraying of the bird is also well captured. Whereas in the Lagrangian, the elements do not disconnect. We might have some element deletion, but it does not really represent the actual phenomena of the bird striking the structure. And this is why usually CEL is the best method, along with SPH, of course. I wish we had the time to present SPH as well, but that would also produce equivalent results to the CEL. I think that concludes our webinar. If you have any questions, please feel free to drop them on the chat box on the right-hand side, and we will answer you right away. Give them a few minutes. So if anybody has questions, they can ask us a question. So one question is, how much computational power would require for running a similar simulation like this one? Well, it depends. It depends on the mesh. Usually CEL is computationally more expensive than SPH and then Lagrangian. And this is because on the domain that Rahul created, the mesh has to be extremely fine, even finer than the Lagrangian model, because the material would have to flow through the mesh. So if your mesh elements are big, then the flow will be irregular, and you would have results that are not highly representative of your actual phenomena. So I would say for CEL, depending on your hardware, of course, if you're using a single CPU, it would take, for this simulation, maybe 1 hour, 45 minutes, 1 hour at max. Another question is, do you provide training services? You provide trainings and services for the company? Yes, we do. We do provide trainings, and we tailor those trainings to the requirement of our customers. And for those who are not willing to invest in manpower to teach them about finite element and the process of doing it, we also do the service for the company. So we perform those simulations for them. Another question is, can we use the FSI work in Abaqus as we do in ANSYS? Absolutely, yes. That's a good question. The FSI stands for Fluid Structure Interaction, for those who do not know the terminology. And this is usually done by combining both Xflow from the Simulia portfolio with Abaqus. So what happens here is we link Abaqus for the structural mechanics, for all the structure behavior, and we use Xflow for the CFD using Latz-Boltzmann formulation. And it's a two-way coupling between the two software. They're very compatible with each other. What happens by two-way, meaning the structure will affect the fluid, and then the fluid behavior will also affect the structure, and so on and so forth. There is one more question. If mass added to projectile nodes or without mass is difference? I don't know if I understood your question correctly, but if you mean using mass scaling, now using mass scaling would increase the mass of the overall problem, the components of it, and it would speed up the simulation time. But be careful, when you increase mass, you also cause more kinetic energy to be generated. So every time you use mass scaling on your explicit definition, you need to look at the energy output and compare the total energy to your kinetic energy. Your kinetic energy must always remain 5% or less, of course, depending on your accuracy that you want. But usually a rule of thumb is kinetic must not exceed 5% of the total energy. If it exceeds, then your results are unrealistic and you need to reduce the mass. Another question is it possible to perform the same simulation in SolidWorks? That's a difficult question. I'm not a SolidWorks guy, but I don't know what SolidWorks is capable of in terms of such dynamic and explicit simulations, but I do not think this is really possible. Now, SolidWorks is not meant purely for simulation. It's a dedicated tool for CAD, but recently there has been many development and the tool is evolving. So I'm not really sure about the most recent update with that. Now, there is another question. Can you provide a webinar using ANSYS for the bird strike using external flow simulation and using the FSI? Thank you for this question. We are really Abaqus guys. We are the partner of the SAW systems. So we're not able to use ANSYS or demonstrate ANSYS in any way. Now, one last question is, what does EVF mean on Abaqus? Rahul, can you share your screen, your Abaqus result, please?
Definitely. EVF basically stands for Eulerian volume fraction. So let me just go on to my Abaqus first, and then I will share my screen. You are talking basically about this EVF void, right? So the EVF void basically means Eulerian void fraction. So what happens is, let me just go to view cut and switch this off. As you see here, it's given in red because within this red there is really no material, or as Abaqus would call it, an Eulerian void. There is an Eulerian void fraction. So there is really no material to that. Because of that, Abaqus calls this a zero volume fraction. But obviously, since we've assigned the bird to the mesh, that's why the material here gives it, like, some volume fraction, showing that there is a material that is interacting with the Eulerian domain. That is what EVF is called, basically.
Okay. There's one question on what kind of element is used when doing this bird strike simulation. You can go to the element foundation. Yeah.
All right, I will go to the element boundary. So as I mentioned again, for you want to know the Eulerian, right? So for the Eulerian, what we do is we go on mesh controls. It's like it's part, yeah. And we go on Eulerian. We go on mesh controls. We click the two cells. and we give it a hex structure. It's really the best mesh when you're dealing with a purely cuboid or a cube shape, volume. We can go with the structured. You can go with sweep, but I don't see the point of really going sweep when you have something like, something as accurate with the structured module. So that's for the Eulerian. For the panel, when you talk about the type of mesh and controls, you can go quad dominated, or you can even go quad and press OK. I don't want to do that now. Those two are fine. But with the element type, you have to go with explicit. You have to go with shell because this was modeled in 2D as a 2D shell. And we don't really want to deal with like quadratic. It's extremely expensive. So you do with linear geometric order.
Yes, I think that's the question. Yeah. Sorry to interrupt, Rahul. I think he's referring to, as an answers for surface, it uses a special type of element for surfaces. And I think what you're referring to here is a shell. What we're using here for the aluminum plate and the fuselage is a shell element, meaning it has no thickness visually to you. But within the definition of the section, we have already assigned a thickness to it. But on the formulation, when the solution comes to the numerical method itself, it's using a shell element, and this reduces computation significantly. There's one more question on the trainings. Is the training available only for companies, or can I join personally? We do offer trainings for companies, and we also offer trainings to the public. We usually do it in terms of batches. So when you show interest to us, we would collect this interest over a few days or sometimes few weeks, and then we'll do a session for everybody, whether you're a company or an individual. And how many nodes does the shell have? I think you can find this from the query, Rahul.
How many nodes does the shell have? Yeah, so I'm just going to go onto the assembly. Yes, I'll go on to the full assembly, and for the whole assembly, I just go on to tool. I go on to tools. I go on to query. I want to go on mesh, and I just press done. And as you see, the total number of nodes is 115,495.
Okay. Thank you. Is there any more questions? Okay, I think that's about it. Thank you everybody for attending. Thank you for your interest and for your questions. Now we still remain at your disposal should you have any more concerns or any more questions. You do have our emails, and the recording will be sent to you. Thank you again and have a good day. Bye-bye.